Welcome to linear algebra. And what we are going to do is we are going to look at an important aspect of linear algebra, which is how do you use linear algebra to solve the problems that involve large scale classification and analysis. And as you know, neural networks have been extremely popular. And in today's class, we are going to look at simple mathematics of neural networks and what do they all mean. So most of you have had some exposure to neural network. Now, one thing to understand that neural networks and deep learning it's not a new concept. So neural network and deep learning is not a new concept. So people have been exploring the ways to do classification, regression, and other types of analysis on large data sets using some type of universal classifier architecture. So if you look at what neural networks are, is a universal classifier. So what that means is we have been talking about regression analysis. We are looking at multivariable regression. At the core, neural network is fundamentally rooted in regression analysis. And what you do is you basically perform optimization so that the weights that are used for classification or function approximation that are optimized. And many of times these function approximations or classification, they may or may not have any physical meaning. So what that means is it could just be some sort of a black box. So a classic way to write a neural network type of mathematical structure is going to be of the form argmin aj, you have f m am, and then you have f2 a2, and then you have f a1, and so on and so forth. And maybe you can have some type of regularization. So I'll explain this just in a minute, what that means. But at the very minimum, what this means is you have a function approximation. And what you do is this function becomes an argument to other function. This function becomes an argument to another function. And every function has some type of parameters. So here you have a parameter a1, b1. Here, if you go on to the next level, you are going to have a parameter a2, b2. And if you go here, there is going to be parameter a3, b3. And at the end, what we want to do is we want to have this super complex function or a functional, which is function of functions. That's why it's called functional, to be optimized so that you can actually provide some input, and input is going to be, so you provide some input and I'm going to call that input as X, and then final result is going to be Y. And again, you can have this structure in multiple ways. So for an example, you can just say certain input and you find out these coefficients A1, B1. So now we are going to find A1, B1, A2, B2, A3, B3. And we are going to find these values recursively. Now, this is very important, what that means, recursively. So we are going to first start with certain values. Then we are going to see if our result is similar to what we anticipate, which means if the left-hand side is equal to right-hand side. If it is not, then we are going to make a decision out of these 6 variables, which variable we need to tweak first so that our result is equal to the result that we desire. And that actually could be because of some type of a regression, or you can actually start with some type of function. So you can do a regression. And then many a times what we want to do is a simple regression is used to find a least square solution. So if you just do a simple regression, then your coefficients will be determined using some type of least square solution. But if you want to find out the sparse solution, you add some type of penalty. So basically, so sparse solution. So you do some type of a penalty, and that kind of leads to this sparse coefficients. And then what we want to do is we want to perform some type of an optimization. Now, what does an optimization mean? Optimization means we are going to look at the change in the output, and then we are going to relate that to the change in the input. In other words, what parameters should I tweak and which direction I should be tweaking? So for an example, should I increase the value of B2 or should I decrease the value of B2? Or should I increase the value of A1 or should I decrease the value of A1? And these parameter tweaking is done using a simple concept which is called as the gradient descent. And what I'm going to do is today I'm going to give you the theoretical construct, but then I'm going to ask you to watch a movie on the neural network. And it's like more like a cartoon film than an actual movie. And that would explain you all the fundamental aspects of neural network, which means there is a math to neural network and there is some sort of a visualization or physical aspect to neural network. So we will start with the very first, something called as the single layer neural network. So what is this single layer neural network? So single layer neural network is something like you have X is equal to A1X. So X1 is equal to A1X. X2 is equal to A2X1. And finally, what you have is your output, which is given as A3X3. So I want you to notice, so you have X1, which is going here. You have X2, which is going here. And finally, you have the output. So this is the output. And now this guy what you have here is the input. So this would look like y is equal to a3, a2, a1, and x. So this is the structure of the simplest possible mapping between the input and the output. So this is like a mapping between input and output. But it is important to note that this mapping is linear. This is not a non-linear mapping, but this is sort of a multi-layer mapping. This is your first layer, this is your second layer, and this is your third layer. So this is, and if you want to look at the structure this mapping actually can be drawn, is you have this initial layer, or these are the initial inputs. So initial inputs could be something like height, it could be weight, it could be frame, small, tall, big, and it could be the circumference, the waist. So, or eye color. So frame, I'm gonna say eye color. Then you can have this first layer, and these lines, they indicate how these are related to different internal layers. So what is the functional relationship between these? Then you will have the next layer, and then there will be some configuration, something like this. And then finally, you are gonna have some type of output. So, and this is, you can say something like team A and team B. So what you are going to do is you are going to make these connections. You are going to actually find out the appropriate values of weights, and then you will be able to get the classification, whether that person belongs to team A or that person belongs to team B. Now, as you can see, this is a multi-layer neural network. So you have multiple layers. Now, if I want to express this as a simple single layer network, then let's start with a simple example. So, example of single layer network. So, example of single layer network is, if you have, we are looking at this example again and again. So you have images of dog and you have images of cat. And what I want to do is to write this into the language of the neural network. I'm gonna say dog indicates +1, cat indicates -1, which means all said and done, if the output of the neural network, if the output of the neural network is above 0, then clearly what I have is a dog. If output of the neural network is below, then what I have is cat. So at the end of the day, if you want to think about it, you can actually change this, and maybe you have cat and you have dog. So you are going to provide some features. So these are the features. And then features, basically you arrange the features, and finally you would see whether it is +1 or -1, and then you will get, if your output is above 0, then you are going to say, yeah, it's a dog. If your output is below 0, then you are going to get, say, cat. So now imagine that we have all the images for dogs and cat. So we have image for dogs and we have images for cat, and each image is like a matrix. Each image is like a matrix. Now what I'm going to do is I'm going to take this each pixel value. I'm going to take this each pixel value and stack these pixel values into a tall and skinny array. So what that means is I'm going to arrange this guy as this is going to go here. This is going to go here. Then this guy is going to go here. This guy is going to go here. This guy is going to go here. And then similarly, I will grab this entire column and stack it over here. So I will actually formulate this tall and skinny matrix. I'm going to do the exact same thing for second value of dog. So second picture of dog, I'm going to do third picture of the dog, third image, and then I'm going to do the exact same thing for the cat values. So these are the cat values. Now, what I'm going to do is, so finally, I'm going to have this huge matrix. And then I'm going to assign all dogs to be pluses. So for an example, these are all dogs. So 1, 1, 1. So there will be 1, 1, 1. These are all cats. So this will be -1, -1, -1. So it will be -1, -1, -1. So then what I'm going to do is I'm going to have a sort of a coefficient A1, A2, all the way to say 1, 2, 3, 4, 5, 6, all the way to A6. So these are the weights. And then remember, this equation is as simple as AX is equal to B. So what I want to do is I can actually, if you look at this X is image of cat or dog. And one thing that I want you to understand is stacking. You can stack it appropriately, but you need to make sure that your labels. Now, just to be consistent, I will actually show you just to make sure the dimensions are correct. This will become like +1, +1, +1, -1, -1, -1. And then what we want to do is we want to perform something called as the pseudo inverse, which is the least square solution And that should be able to give me, so I'm going to call this system is, and in the least, just to be consistent, I'm going to write this down as you have A x is equal to y. And then to find A, I need to actually find in it, I need to invert this, which is y times x star or x plus. This guy is called as the pseudo inverse. And the way to find this pseudo inverse is using just a dot multiplication. So I'm going to explain this once again very quickly. So what we do is A is all these weights. A is all these weights. This guy, what we have here is X. Now please understand, X is an M times N matrix. It's a rectangular matrix. It's not a square matrix. So this is a rectangular matrix. So this rectangular matrix cannot be inverted. So what first needs to happen is we need to multiply the left-hand side and the right-hand side by the transpose of X. So you're going to have X transpose is equal to Y X transpose. So now once you have this X transpose, this becomes a square matrix. And since this becomes a square matrix, you can actually invert this. So to find the value of A, what you do is you have Y X transpose, and now you are going to do X transpose and find the inverse of X transpose, and that will give you the answer of A. So that is something. So this is the simplest way to build a single layer neural network. So this is the simplest way to build a neural network. And what I'm going to do is I'm going to talk about this. I will actually show you a very simple example. And the way this single layer neural network can be expressed is something like this. So, and this is the input, and this is something called as the perceptron. And you can actually be more creative, and you can use different ways to solve this problem. So this is like you can use a least square solution, or if you want a sparse solution or a L1 solution, you can actually use the L1 solution, and the command for that is something called as lasso. So you can use either an L2 solution or you can use L1 solution. So you can use whatever type of solution that kind of makes sense. So now the next part is I will show you the result of a single layer neural network. So the problem here is the results are not that great. So single layer results are not very good. And the reason for that is neural network are piecewise linear functions with some type of activation element. And that is the basic premise behind the neural network. Is like you can cascade these different linear functions that are piecewise linear, and you should be able to get the answer. So what that means is to overcome the limitation of a single layer neural network, what we do is we go on to something called as the multi-layer neural network. So in multi-layer neural network, what you want to do is you want to have something called as the linear function. So you are going to have a weight and a bias, and then you are going to have some type of mapping. So you have piecewise linear function, and then we use a non-linear mapping. Now you can use f of x is equal to x, that is linear. You can use f of x is equal to 0 and 1 for x less than 0, for x greater than 0. This is called as binary step. Then you can use f of x is logistic. Is logistic, which is called as the soft step. And then you have f of x tan h, and you can have, this is a very famous activation function, which is f of x is equal to 0 x for x is less than equal to 0 for x is greater than 0. This is called as the rectified linear unit, which is also called as ReLU. And this is a very famous activation function. So probably what that means is if you want to show this activation function, this is going to be something like this, and then it's going to be like this. So this is the ReLU. Now, it is important to understand that when you have more than one layer, so it's very important, for more than one layer, the standard optimization techniques do not work. So for more than one layer, standard activation techniques do not work. So what we need to do is essentially we are trying to optimize a higher dimensional space. So because the space, optimizing the space to be optimized is higher dimension. And what we need to do is we need to use some type of numerical technique. And for numerical technique, what we use is we use something called as there are two important optimization components. One is like gradient descent. It is like variant is stochastic gradient descent, which is called as SGD, and back propagation. And these are actually built in a simple MATLAB or Python package, and they are used very widely to train the neural networks. Now, the issue here is we want to actually also look at the connectivity between layers. So connectivity between layers means how are we going to process the output of the previous layer, and how are we going to feed that output of the previous layer to the next layer. And even though everything here is well implemented in a software like MATLAB and Python, but it is important to note that at the end of the day, the neural network is a universal approximator. What that means, it finds the relationship from between input and output based on the data. So what you have is you have this data. In this data, you have certain inputs, you have certain outputs, and you are done with labeling. So you know that certain data belongs to what data. So what usually happens is basically you take part of this data and hold it. And what you do is you basically train the remaining data and then you test it on this data. So what you do is you basically train your neural network, test it on this, and then basically you have a trained neural network. So when the new data set comes in, this new data gets fed to the neural network that you have trained, and this neural network should be able to give you the output. So one important component of this training is something called as the back propagation. And at bare minimum, the back prop is nothing but a variation of optimization algorithm where the weights or the coefficients are tuned so that you get the best possible result. So we are going to talk about something called as the back propagation. So what do we mean by backprop? So in the single layer neural network, we used least square regression. So single layer network, we used least square or lasso, which is L1. So L1 norm type regression. But when you have multi-layer network, what you want to do is you want to actually come up with some sort of algorithm that can simultaneously optimize more than 1, 2, 3, 4, 5, 6 weights. And as you increase, so there is something called as the curse of dimensionality. As you increase the dimension, then clearly the amount of computational time that we need to get a neural network converge and understand, and then basically uh, that becomes almost impossible. So what you want to do is you want to actually make sure that you want to keep track. So keep track of computational complexity as we perform these large scale optimization. So, and at the end, what we want to do is we want to actually come up with some type of uh, trade-off between the computational complexity and then how we want to achieve some meaningful results in the time that is given to us. So what I want to do is, at this point, I want to take a very simple example, and I want to actually explain this how this back propagation algorithm works. And one thing I want to tell you is I'm gonna give you the math in today's class, and I'm gonna ask you to watch some videos before you come to next class. And just like the linear algebra videos that were presented or that were created by one blue, three brown, there is an excellent 4-part video series on neural networks and deep neural networks. Once you watch that, you will get a geometric significance of all these steps. So let's see how this back propagation algorithm works for a single node, one hidden layer, network. So what this means is y is equal to g b is equal to g f of x comma a b and these are the different functions, and this is a mathematical representation of single node, one hidden layer network. Now what we are going to do is A and B are the constants, and I want to find out the error. So I'm gonna say the true value is y, and I have another value y0. So basically y0 is, so let me put it this way, y0 is the true value and y is the value computed by neural network. So your error E is equal to 1/2 y0 minus y square. So this is the actual error, and the objective here, objective is to find out the values, find A and B so that error is minimum. So find the values of A and B so that the error is minimum. So this minimization implies that you need to take the derivative of error, which is the partial derivative of error, partial E by partial A, that can be written as minus y0 minus y, and clearly you have these y's, so you need to do dy by dz, and you need to do dz by dA. Now this needs a little discussion, so please try to understand. Finally, your function is y is equal to g, y is equal to g of z b. And then if you look at what that z is nothing but this f of x. So this is nothing but z. So you have zb. So now if you want to take the derivative with respect to a, so first you need to take the derivative with respect to z, and then you need to use the rule derivative of z with respect to a. So what that means is, it is important to note that this derivative is comprising of the chain rule. So this is like a chain rule, and I want you to actually focus on this product which is written here. So basically, the product that I want you to focus on is dy by dz and dz by dA. dy by dz and dz by dA. So we want to find this out by using the explicit iteration. So a k is equal to, we want to find out the values of a and b, is equal to a k minus delta partial e by partial ak b k plus 1 is equal to B key minus delta partial E divided by partial P key. So this delta that we talk about, this delta is called as the learning rate. Now what that means is you are you are making these small teeny tiny changes, and you are actually performing these computations continuously. So what you are going to do is you are going to iterate. So we are going to perform these iterations till you achieve some kind of convergence. So this iterative technique is going to go on till you achieve some good results and good convergence. So the back proposition works something like this. A neural network is specified along the label training set. Second, the initial weights are set to random values. And it is very important to note that you cannot initialize the initial weights to 0. Otherwise, it will not work. The third thing is training data is run through the network to produce an output. Where we have the ground truth, why not, is the label or ground truth. Or label data. The fourth one is you are gonna actually get the derivative with respect to each weight and using the propagation formula that is shown over here. So we are gonna use this formula using backprop formula. And then we can actually, for given learning rate, network weights are updated. And then basically what you do is you repeat this process till you achieve some kind of convergence, or you specify number of iterations, say 1000, 2000, 3000. So let me quickly go through an example. And this actually involves the activation function. So I'm going to assume a linear activation function. So linear activation function. And this linear activation function is given as f of, so this linear activation function is a function which is alpha, and I'm going to approximate this whole thing is maybe is equal to alpha multiplied by zeta. So my linear activation function is given by this. So if you look at the formulation that we talked about a moment ago, I'm going to substitute this linear activation function, and then I get the value of z is equal to ax and y is equal to bz. So please pay attention here. This is the equation that we are focusing. So you have f as one function, which is nothing but z, and g, which is operating on something else. And then you have this activation function. So now we can compute the gradients. So something like partial E by partial A equal to minus y naught minus y dy dz dz dA is equal to minus y naught y bx. Partial E partial B minus, and then I'm going to do dy dB is equal to y naught y a x. Now with the current values, you start with a and b. You got the output values. So, and then what you do is you are going to perform these iterations. So, and every time you are going to find the values of error and then run through numerically. And this exact technique actually can be extended for a deeper net or multi-layer network. So for deeper multi-layer net, y ui divided by dzm dzm dcm minus 1 ez2 dz1, and you have dz1 d. So this cascade of derivative. So you have this derivatives uses composition and chain rule. And now the objective is we want to find out the matrix element, and then we need to solve these. So typically, since you are going to solve, these are going to be all matrix coefficients. So what you're going to have is you're going to have a W vector, which is the weight vector, k plus 1 is equal to Wk minus delta E, where you have gradient of error delta E. And what you do is you run this through the algorithm, and for each iteration, k plus 1 is equal to partial E by partial Wk. So this is the basic math behind the neural network. And let me honestly tell you, this math behind the neural network is pretty boring. Now, but this is very important. So at this point, what I want to do is I want you to visit this. Let me share my screen. So I'm going to share my screen. And I want you to go to this 3 blue, 1 brown. So 3 blue, 1 brown. And I want you to go to this website, and you will notice that there is this something called as neural network. So now I would really like you to kind of watch these physical or geometric interpretations of neural networks. So first lesson is about what is neural network, and there is an example which runs on the handwriting recognition. The next thing is the gradient descent, which we talked about in mathematical terms. Then the next part is how do you compare the performance of the neural network? What that means is your output, and how do you compare that with the actual theoretical output? And then the back propagation. And then finally, you will see the stochastic, the gradient descent and stochastic gradient descent. So these 5 chapters give you a very nice visual interpretation of what neural network is, how they work. And let me tell you that there is not math in it, but I already discussed the math, which is a little bit boring. But once you watch these videos, all will make sense. And with that, in what I would do in next class is I would jump on to MATLAB, and then we will actually work out the problems, and then we will see the various applications of neural networks. So for an example, how do we use neural networks for system identification? What do we mean by a recurrent neural network? What are the autoencoders? And then what are the different types of neural networks? And something I would emphasize that nowadays there is a lot of emphasis on deep fakes, wherein you have the images or the videos, they are so realistic, but they are not really of true people. So those are generated using something called as the generative adversarial networks, so or GAN networks. So we will look at the GAN network, and then we are going to look at some classic applications of neural networks. But before we do those MATLAB exercises, I want you to have a deep understanding of how the equations that we discussed in today's class actually relate to the practical application of neural network in some type of a visual form. So it is absolutely essential for you all to watch these videos, and they are fun to watch, and come prepared next class so that we can actually work out some problems. And with that, I am gonna